The next speaker is Márton Naszódi, and he will speak about covering convex bodies and the closest vector problem.
Спасибо, здравствуйте. I'm very happy to be here in Moscow, except that I'm in Budapest, but I guess some other people have made that joke. So honestly, it's really sad that I cannot be in Moscow right now. It would be very nice. So I'm going to talk about a joint work with Moritz Wentzen from EPFL, Lausanne. And it's going to be about covering convex bodies and the CVP, the closest vector problem. So first, let me introduce this problem. So this is some sort of an integer programming problem, and it goes as follows. So we're given a lattice and a target vector t in Rn or Qn, and our job is to find the closest vector, the closest lattice vector to the target t with respect to some norm. Okay, so you're given a vector which is not a lattice vector, and you want to find the closest lattice vector in some given norm. And while this is a difficult problem, well, as integer programming problems usually are, it's NP hard. So even it's NP hard even if you only consider LP norms. If you fix P and consider that kind of LP norm in Rn, then it's still an NP hard problem. So it makes sense to look for approximate solutions. So what I'm going to be talking about today is approximate CVP solvers. So solver just means an algorithm. So what's the task now? Instead of trying to find the best vector, the closest lattice vector to T, I'm just going to try to find a vector which is almost as close as the closest, as the minimum. So there is this 1 plus epsilon multiplicative error term there that is allowed. Okay, and we call this problem the 1 plus epsilon CVP, closest vector problem. And sub k, the subscript k means that I consider it when the unit ball of my norm is some origin symmetric convex body k, or in the particular case when we are in LP spaces, I just put CVP sub little p. Okay, so that's the algorithmic problem, and let me tell you a bit of the history here. It's not going to be extensive at all, just some highlights. So first, Blömer and Neve, building on the works of Ajtai Kumar and Siva Kumar, gave an algorithm, an approximate CVP solver for all P. So it works for all LP spaces, and the running time is 1 over epsilon to the 2n. So here, let me just point out that exponent 2n there. And then Dadush, again, building on the works of Ajtai Kumar and Siva Kumar, gave an algorithm of the same running time, but this time one that works for any norm. I'm not going to talk about results for L2. There are much better results, but we're not interested in those, not going in that direction. So let me mention another paper by Eisenbrand, Hanle, and Niemeyer, where they consider the L infinity norm specifically, and they used the Blömer and Neve algorithm and boosted it and got a much faster algorithm. So of course it's a very special case. It's not LP in general, but it's L infinity. So the unit ball is the box in Rn. But now we have log 1 over epsilon to the power n as a running time. And the main idea of their algorithm was to first take the unit ball of the norm, which is, well, it's the cube. So take the cube and divide it or chop it up into smaller sets. Well, not necessarily cubes, but smaller rectangular shapes, and run the Blomer-Neve algorithm for those smaller sets, but with a bigger error. I will discuss it in more detail later. And one more thing, the best result so far is by, the best general result is by Dadush and Kuhn, where they gave, coming from a really different direction with a very different approach, they gave an approximate CLDP solver for any norm, and now their running time is 1/epsilon⁴. So they managed to get that 1/epsilon to the 2n, the 2n exponent down to n, and note also that the dependence on n is still 2 to the big O(n). Okay, so let me just go back first. So really, I'm pretending here that I'm giving a talk about discrete optimization and about an algorithm, but what I'm really going to be interested in this talk is this covering problem that Eisenbrand, Hanlon, and Niemeyer came up with. So let me introduce this covering problem, really our main topic today. So case of convex bodies, it's a compact convex set with non-empty interior. And our task is to cover it with smaller bodies, as few as possible, so that the following holds, that first of all, these QIs, these smaller convex bodies, cover K. However, they don't stick out too much. So when you enlarge each of them by a factor 2, so that's what I just denoted by this circle dot, 2 circle dot QI. So when you enlarge by a factor 2, they still remain in this slightly enlarged copy of K, 1 plus epsilon times K. Okay, and the question is, this is a general question. You can forget the algorithmic problem and all that. Just consider this: given a convex body K, and how small can this capital N be? So how few convex bodies QI can you take so that they cover K, their union covers K, but when each of them is blown up by a factor 2, they still remain in 1 plus epsilon times K. And well, when I talk about this blowing up, this enlargement, I mean that you take a homotety with center at the centroid of QI. Now, the centroid it's the center of mass of QI. If you're not familiar with the centroid or center of mass, then it's okay, because usually these QIs are going to be really centrally symmetric bodies, and then the centroid is just simply the center of symmetry. So that's the point. Okay, so that's the problem. I mean, if it was a real talk, I would stop here for a moment and look around and ask you, isn't it pretty? So I'm asking you, isn't it pretty? But I'm assuming you find it pretty. So first, some easy easy bounds for this problem. So first of all, we assume that the centroid of K is the origin, and then K can be there is a 2 epsilon covering of K by, well, very roughly 1/epsilon to the n translates of, well, this K intersection minus K times epsilon. So you take this symmetric body and the epsilon times it. This is a very standard, very simple epsilon net argument, and it doesn't require anything anything new, anything fancy. Then again, by a rather standard argument, you can show that it's enough to consider central symmetric QI. So instead of whatever number you had, you may lose this 10 to the n factor. So your capital N may go up by a factor 10 to the n, but apart from that, you can assume that these QIs are centrally symmetric. Okay, and so the question here is, well, we're not really interested. We're interested in the dependence on n to some extent. So, for example, we don't want the dependence to be something of order n to the n, but as long as it's constant to the n, it's okay. What we're really interested in is the dependence on epsilon. So are we gonna get 1 over epsilon to the n or something better? And so here's an immediate lower bound that, well, you cannot really go below 1 over epsilon to the n half. If you consider the Euclidean unit ball, so here I just denoted it by b sub 2n. So the Euclidean unit ball, it really needs 1 over epsilon to the n half bodies in a 2 epsilon covering. You cannot do better than that. Okay, so that was our first definition, and there is one more I'd like to introduce, which is the modulus of smoothness of a convex body. So this definition comes from function analysis and is heavily used there, but you don't really need you don't need to know it very well. I'll give you the definition, and I warn you, don't read the definition here. This is just a decorational element there, but really just read the yellow part at the bottom of the page. So what this modulus of smoothness is the following. So you're given a convex body. Think of it as the unit ball of a norm. Okay, so you're given a norm in Rn. Take the unit ball, and let's assume that it's so the modulus of smoothness is going to be a function of k. Sorry, a function of tau. So it's a real-to-real function. And consider the following. Take a point x on the boundary of the ball, and now take a tangential direction y at x. Okay, so y, let's make y, take a y which is parallel to some tangent line of k at x. Okay, so x is a point on the boundary of the ball. Okay, so x is a point on the sphere of our norm sphere, and we move away from x in some tangential direction. Then, of course, if I move away in a tangential direction, then the norm will become bigger than 1, right? So x plus tau y and x minus tau y, they're all at least 1. I mean, they can remain 1 if the body is not strictly convex, but it will certainly not be small, less than 1. Okay, and now if you just substitute into the definition up there, you get this yellow formula. So what does it mean, the yellow formula? Well, let's assume that our modulus of smoothness is very nice, which means the body is really nice, very smooth. Smooth means that it's very close. The boundary is very close to the tangent planes. So let's assume that we have this modulus of smoothness, rho of tau, less or equal to tau squared. So here in the modulus of smoothness, it's really the exponent of tau that matters. So let's say we have tau squared there, the best exponent. And that means that in the yellow formula, if you move away by a length root epsilon, so tau is root epsilon, you're only getting away from the origin by 2 epsilon. Okay, so you moved in the tangential direction by root epsilon. Root epsilon is big, right? If epsilon is a small number, and root epsilon is big. So you moved in a tangential direction by root epsilon, and the norm didn't grow by more than 2 epsilon, which is very little. So this is the miracle of good modulus of smoothness. And this is what we will heavily use. Okay, and so we have two main results. The first one is that if you have a norm for which the modulus of smoothness is good, so this exponent up there is big, it's, well, let's say it's 2, then you have a good 2 epsilon covering. So good meaning like with few bodies. Okay, so here's the theorem. So if K has modulus of smoothness at most tau to the Q, the constant factor doesn't really matter. Then there is a 2 epsilon covering using at most, well, 2 to the ON, 1 over epsilon to the N over Q convex bodies. Okay, so what it means, well, I didn't state the modulus of smoothness for LP balls. You can look it up in any book, but if you just simply plug in those well-known formulas for the modulus of smoothness of LP balls, then you get that if P is greater than 2, or equal to 2, like the Euclidean case, then this Q, the exponent in the modulus of smoothness is 2. So you get 1 over epsilon to the n half. You have a covering of the ball, not by 1 over epsilon to the n pieces, but by 1 over epsilon to the n half pieces. And that's the big thing here. And for other LPs, well, P's between 1 and 2, you have n divided by P. So as if your P is close to 2, then it's essentially n half. The further away, the closer you get to L1, the less good your modulus of smoothness becomes. Okay, and as I mentioned before, for the Euclidean ball, we have this matching lower bound. So this is an upper bound, 2 to the big O n 1 over epsilon to the n half. But for the Euclidean ball, we actually have essentially the same lower bound. Okay, so that's our first result. If you have good modulus of smoothness, then you can cover the ball nicely. You have a 2 epsilon covering. Now, our other result, the second result, is that if you have a good covering, a good 2 epsilon covering, then you get a fast approximate CVP solver. So here's the statement. Let's say you have a 2 epsilon covering of K. So K is the norm ball with n bodies. Then you can solve CVPK. Well, there's a little change in the error, but it doesn't matter much. In, well, very roughly n log 1 over epsilon, using this many calls to a 2 approximate CVP solver. Okay, so again, let me stop here. So here, instead of an 1 plus epsilon CVP solver, you're calling a 2 approximate CVP solver. So now that means that if you, so remember here at the bottom, I wrote the Dadush and Kuhn result at the bottom of this page. So the 1 plus epsilon CVP solver of Dadush and Kuhn, which works for any norm, is of time 1 over epsilon to the n. Now, but if I have epsilon equals 1, which means 2 approximate, right? 1 plus 1 is 2, supposedly. So then the time is just 2 to the big O n, right? If epsilon is just fixed constant, then the time of the Dadush-Kuhn algorithm is just 2 to the constant times n. So our theorem states that this is how many times you need to call n times log at 1 over epsilon times you need to call, say, the Dadush and Kuhn algorithm with epsilon equals 1, and you get an epsilon, 1 plus epsilon solver for K. So this is the corollary, just simply using what we previously stated, the first main result, which says that for LP, there is a good good covering. Okay, so now is it okay? I'm going to stop here for a second. Is this clear so far? Are there questions? You can turn on your mic and shout your question in the
Yes. Hello,
Yeah,
Marty. There is one question. Actually, can you return to the previous slide?
sure.
I don't understand that
Hi,
for
Grisha.
hello, for LP spaces,
Yeah.
you have this constant. It's not 2 to the O over n. So if this constant for LP spaces is of order p, so it must be p to the n.
Sorry, say it again.
So in your theorem, the constant in modulus of smoothness for LP spaces is
Yeah.
actually p or square root of p, doesn't matter.
Yeah. But we don't care about that for, I mean, it's just for fixed p, it's just one. For
Okay,
fixed p, yeah.
For fixed p.
No, I'm talking about fixed p. So n and epsilon are not fixed, but p is
Okay,
fixed.
so
Yes.
I mean, this corollary, we understand that we fix p, and it's not a uniform bound for all p.
No. That's yeah. No. The big O. Yeah, you're right. The big O depends on p. That's right. Yes.
Okay, thank you.
Yeah. Thanks very much for pointing that out. That's important. So here I allow epsilon to go to 0, n to go to infinity, but p is just fixed for any. Yeah. Okay. Thanks, Grisha. Okay. So let me give you a sketch of this proof. So we have let's say an origin symmetric convex body, and assume that its modulus of smoothness is nice. It's c times tau to the q, and then I need to show you this formula that we can cover it by this many convex bodies. So very roughly, we can cover it by 1 over epsilon to the n over q bodies. And for simplicity, I'm gonna consider the nicest case when oops, yeah, I didn't mean a 1/2 there. Sorry, replace that 1/2 with a 1. So when the modulus of smoothness of tau is at most, so rho of tau is at most tau to the second power. So it should be tau squared and not tau square root. So tau squared. And then I take delta to be root epsilon, or well, roughly root epsilon. I make sure that epsilon is small enough so delta minus epsilon is still at least delta half. And what do I need to do? I need to give you a 2 epsilon covering of my convex body K. So what I will do is I will just do it first around a point in the neighborhood of some point of K, and then somehow globalize it. Okay, so here is my point P. Okay, so we fix a point P on the boundary of our convex body K. And T sub P is the supporting hyperplane, or a supporting hyperplane of K at P. Okay, and I define this BP, which is those points on T sub P that are close to P, delta close to P. So delta is roughly square root of epsilon. Okay, so this if let's say if K is 3-dimensional, then T sub P is a plane. It's a 2-dimensional plane, and BP, B sub P, this blue thing, it's a disk. It's a 2-dimensional disk in 3 space. Okay, so that's B sub P. And the main claim is the following. So it's a rather large. It's large in the sense that its radius is delta, and delta, don't forget it, it's about root epsilon. It's not epsilon, it's square root of epsilon. Okay, so we have this disk, this blue disk, B sub P. And I claim that now, if you take the convex hull of the origin and this B sub P, which is a cone, I didn't draw it, there would have been too many things on the figure, but take this cone with apex at the origin and the base is B sub P. Then that cone contains an important portion, a big portion of the boundary of K. So what do I mean by big portion? Well, I take the delta minus epsilon radius ball around P and intersect the boundary of K with this ball. Okay, so this BDK intersected by this green ball. This is on my picture, it will be some arc on the boundary of P. And I claim that this arc is contained in the cone whose base is B sub P. Okay, well, let's check it. And I claim this is rather simple. You hardly need anything more than just the definition of the modulus smoothness. So let's take some point inside this ball on the boundary of K. So that's Q. And I need to show you that Q is in the cone, is in this cone. Okay, so first of all, I intersect the whole picture by this two-dimensional plane spanned by P and Q and the origin. So so what you see is really the full picture, this two-dimensional picture. And what I didn't draw there, again, because of lack of space, is S prime, which is you just project S to the unit ball, just centrally project from the origin. So just normalize S. So now it's on that arc. And now, since I'm running out of time, I will skip some detail here. The point is just simply using the modulus of convexity, the definition, you obtain that this S prime is further away from P than Q. So if you start going clockwise, you walk clockwise from P along the boundary of K, then you will first hit Q, and after that you will hit S prime. And so we won because that means that Q is contained in the cone. And this is just a minor thing that you actually to prove this, you need the monotonicity, some sort of monotonicity properties or property of the norm in Minkowski planes. Okay, so that was this claim that this cone contains this big part of the boundary is now proved. And now let me complete this proof. So what's our goal? We want to give a 2 epsilon covering of the whole K. And so what we will do is first, we had this cone, this convex whose base is B sub P. But instead of that cone, we will now take a cylinder whose base is the same. It has the same base, but just make it a big cylinder that contains the cone and has the same base. So it's a horizontal cylinder on the picture, and the other end, the other base is through the origin. Okay, and so now I will just logarithmically slice this cylinder. So this is a cylinder. One of the bases of the cylinder goes through the origin. The other base goes through P. And so, well, the P has norm 1, the origin has norm 0. And so I will take the first half from 0 to 1/2 of the cylinder. That will be my first slice. Then I take from 1/2 to 3/4, that's my second slice. Then from 3/4 to 7/8, that's my third slice, and so on. And this way I slice it up logarithmically. And you can see that now if you enlarge these slices by a factor 2, these slices will remain in K. And now let me skip the part how you extend it from just one point and the neighborhood of this one point P to a covering of the whole K. But I would say it's a really simple standard argument. And by this, you get a nice 2 epsilon covering of K. Well, I can only state our second result, which I actually stated, which is that if you have a good covering, then you get a fast 1 plus epsilon CVP solver. I won't be able to show you the proof. I was kind of prepared not to be able to show you the proof. So let me just pose a question which seems completely unrelated to everything I've talked about so far, but actually it is related, and it's a very basic question. I I have an 8-year-old daughter and a 6-year-old son, and I really wonder how they never asked me this question so far, but well, maybe they will. So here's the question. So take the Euclidean ball, and I'm just looking for a convex polytope that epsilon approximates the ball. So, well, this is what I mean by epsilon approximation. And my question is, well, there are many nice results about how well you can approximate the ball with a polytope if you are only allowed, your polytope is only allowed to have a certain number of vertices or a certain number of facets. And then very roughly, you can do 1 over epsilon to the n-half. So if I said that how well can I approximate okay, I want to approximate the ball with a polytope with this epsilon error as on the formula. How many vertices does it need to have? The answer is, well, you can do it having only 1 over epsilon to the n-half vertices. If I ask the same question with facets, it's the same answer. You can do it with 1 over epsilon to the n-half facets. But what if I'm interested in the total number of faces? So which you can call the combinatorial complexity. Can you do it with 1 over epsilon to the n-half total complexity? And I'm even interested in a constant epsilon. So take epsilon equals 1/2. Here is the question, baby question. Is there a convex polytope which contains the radius 1/2 ball, Euclidean ball, is contained in the radius 1 Euclidean ball, and has constant to the n total number of faces? So thank you. And I'm sorry I went over time.
Thank you for the talk. Are there any questions?
Oh, I have one question, but I think it's better to ask it privately, not here. So, or if we have time, you can go to the 8th slide. Slide is number 8.
Slide 8, okay.
Yeah.
Voila.
Oh, here. So you claim that by monotonicity, the norm of the S prime minus P is bigger than norm Q minus P.
No,
Yes?
the other, by the modulus of convexity, it's bigger. And then by monotonicity, we get that. So using the modulus of convexity, we compute that P, that S prime P, S prime is farther from P than Q from P. And then monotonicity gives that, that clockwise, walking clockwise, S prime is farther than Q from P.
Actually, I do not understand why you have such construction. So why Q? So why Q could? Okay. So is it possible that Q belongs to the arc between S prime and P?
That's exactly the goal. If we can show that Q is in the arc or on the arc between S prime and P, then we are happy, because that means that Q is contained in the cone, in this cone.
Okay, I don't understand why it's on this arc or vice versa, not in this arc.
Okay, so it will be on this arc, and the way to prove it is that using the modulus of convexity, we show that from P, look from P, in the norm, S prime is farther from P than Q from P. We know that Q from P is delta minus epsilon.
The thing is
because
that the tangent,
that was the definition of Q.
Márton, so you have two directions of P and direction of, I would say, S minus P, tangent direction to the P, to the ball point P. And the thing is that if one tangent to another, then the second is not tangent to the first one.
Yeah. But I don't use that. I'm not using
Okay.
that. All I'm saying is that's right. Okay, so if you want this, we can discuss it in person. But
Yeah, we can discuss
the point is here, I'm really just using the definition of modulus of convexity to get that S prime minus P norm is bigger than Q minus P norm.
Okay.
That's the whole point of this proof. And yeah. Okay.
Let's discuss it later. Thank you.
Thank you, Marci, again.
Thank you very much for